In this video, we're going to look a little bit more at even and odd functions. Now, first thing I want to mention is that most functions are neither even nor odd. They don't fit into either of those categories. So it's not like the integers where half of the integers are even and all the rest of them are odd. With functions, the typical function is neither even nor odd. It just doesn't have, these are special properties that most functions don't have. Other thing I want to mention at the onset here is that sometimes in math, we're looking for something that's not there. What I mean by that is that there's a tendency for students when they're learning math to somehow look at a really simple statement and think that it must be saying more because it couldn't be as simple as it seems to be, but actually it frequently is really simple. And so always consider the possibility that, that something is just right there, easy to comprehend, and that you're not missing anything. It's just that that's all there is to it. And that's the case with even functions. Now, symbolically, you can sometimes get a little bit hung up with the language because like any language, you have to get familiar with it by repetition. Basic defining concept of an even function is that if you replace the input with its opposite, you get the exact same output. So e of the opposite of x is the same thing as e of x. But again, unless you're kind of fluent in this from months or years of experience, it may not be saying a whole lot to you. The reason we call these even functions is because you can think of sort of the archetype, the archetypical even function as being a power function with an even exponent. F of x equals x to the 10th, for example. 10 is an even number. It's a multiple of 2. And if we calculate f of, let's say, 2, I want to keep the number small. I didn't choose 2 because it's an even number. I could have chosen 3, but I wanted to not have the power get too big here. F of 2 is 2 to the 10th. 2 to the 10th is what happens if you multiply 10 2's together, and you get 1024. Now, you can do the multiplication if you like, or take my word for it, but if you were to multiply 10 negative 2's together, as you probably know from working with negative numbers, if you have an even number of negative numbers, the end result is positive. The negatives cancel out in pairs. So if you looked at, we'd have 5 pairs of negative 2's multiplied together. Each of those negative 2's multiplied together would be positive 4. You multiply 5 4's together, you get 1024. If we were to look at x to the 12th, or x to the 32nd, or x to the 1 millionth, all of those would be even functions. Those aren't the only functions that are even. It's not just the power functions that have an even exponent. So, for example, in trigonometry, if you have any experience of trigonometry, it turns out that the cosine function and its reciprocal, the secant function, both of those are even functions. The absolute value function is also an even function. And there are also some more obscure exotic functions that you're not likely to run into that are even functions. But again, an even function is kind of a strange thing in the sense, I almost said oddity, but an even function is an unusual situation. Most functions are not even. Now, the functions that are not even, most of them are not odd either, but there are some that are odd, and the defining concept of an odd function is that if you replace the input with its opposite, you get the opposite output. So for example, I used E for even function back here and O for odd function there. You can use, of course, whatever sort of symbolism works for you, but that seems sort of natural to me. an example of an odd function. Go in and create myself a function here. Call this one g. Well, we could go to either the 9th power or the 11th power. Let's try the 11th power since we just did the 12th power. It turns out, so let me see, almost there, x to the power of 11. Okay, so g of x equals x to the 11th. If you multiply 11 x's together, that means that if x were a negative number, you would have an odd number of negatives. And so as you go through, you would cancel out the pairs. So for example, if we were to look at, you can copy, paste, and do some manipulation here. Copy, paste, and then go in and do g of 2 for starters. G of 2, I probably don't even need a calculator for that. The 10th power was 1024, twice that would be the 11th power, 2048. $2,048. Okay, so if we were to replace 2 with negative 2, we'd be multiplying similar to the multiplication that we had for the 10th power of negative 2 rather. 10th power of negative 2, so actually let's just go ahead and look at it that way to bring out that little fairly trivial piece of information, but sometimes thinking about these things that you may not think of on a regular basis is worthwhile. So let me give you here a second. Parentheses. Oh. Here we are. So, okay, so here we have g of negative 2, which is negative 2 to the 11th power. So I want to point out, go back up here to the f of negative 2 at negative 2 to the 10th power. You'll notice I put that in parentheses. So the parentheses are very important in the notation here. If you use a calculator without putting in the parentheses, it will raise 2 to the 10th power and then make it negative after that. I'm sure if you've been told that before, maybe remembered that, but it's really important. It's a common mistake to forget the parentheses in this situation. Now it turns out that if you don't use the parentheses for the g function here, you'd actually get the right answer, but maybe for the wrong reasons. So if I don't have parentheses, and it's actually the opposite of 2 to the 11th power, whereas what I've got written out here, negative 2 to the 11th, is 11 negative 2's all multiplied together, which is different from just taking the opposite of 11 2's multiplied together, though you do get the same result, though you go different paths to get there. Okay, so I just want to point out that, well, this would be the same thing as, take a second here to type this in here. So while I'm working, you probably aren't seeing the little window that I have because you should be seeing the original document, and I'm temporarily working in a window that's opening up here. So just bear with me while I'm cleaning this up. Okay. So the 11th power of negative 2 is negative 2 times the 10th power of negative 2. And having established the fact that the 10th power of negative 2 is positive, then we have a negative times the positive, which of course is negative. So what we end up with is negative 2048. And there we are. Any power function where you just have x raised to a power, if that power is an odd integer, and it actually turns out whether it's a positive odd integer like 11 or a negative odd integer like negative 11, in either case it turns out that that's going to be an odd function. Also turns out that if you add a bunch of odd functions together, you get an odd function. And if you add a bunch of even functions together, you get an even function. So polynomial functions where all of the exponents are even functions, and polynomial functions where all of the exponents are odd functions. But in most cases, the polynomial function is going to have a mixture of those, and it will be neither of those. So, for example, let me create something here, P for polynomial. Make it simple, x squared plus x. So the polynomial function P of x equals x squared plus x. Well, x squared by itself would be an even function. X by itself, that's the same thing as x to the first power, which is an odd number, so it would be an odd function. It turns out that this function is neither even nor odd. If it were even, then that means that if you switch the input to its opposite, you'd have to get an output, which is same as the original. Let me see what I'm trying to copy here. Okay, I want to copy that. So if we go down and look, for example, at P of 5, which is 5 squared plus 5, which is equal to 30. So P of 5 is 30. So if we look at the corresponding input for negative 5, so you copy that, and again paste. You go and do some changing. Okay, so make that negative here, parentheses around. So when in doubt, use parentheses, which is what I'm doing right now. I'm putting parentheses around my negative 5. So you can see what I'm doing here. P of negative 5, so I'm comparing P of negative 5 to P of 5. If the function is even, I'm going to get the same result that I got before, which is 30. If the function is odd, I'm going to get the opposite of the result I got before. In other words, I'm going to get negative 30. Well, if you do the calculation, you see you don't get either of those things. If you square negative 5, you get 25. And then if you add negative 5 to that, you of course get 20. So there's no obvious connection between the output in this case and the output when we plugged in 5. So P of 5 and P of negative 5 went to places that don't seem to be connected to each other in any obvious way. And so this just doesn't have that property of being an even function or an odd function. Now, if it had worked, that wouldn't prove that the function is even or odd, but the fact that it didn't work in either case definitely disproves the notion that the function is even or odd. Maybe dig down a little bit deeper in that. Let's look at a different function here. So I'm going to call this one, a second here. Okay, and there we are. R of x equals 1 over x. Now it's also possible to write this as x to the negative first power, and since -1 is an odd number, odd integer, that would suggest an odd function. And it turns out this is an odd function. Now we could check that by looking at what happens here if we say look at R of 7, which of course is 1/7. And then if we compare that to having the opposite input, so I'm going to change 7 to -7. So R of 7 is 1/7, 1/7. R of -7 is 1/7. That's what the function is. It's just a reciprocal 1 over the thing. 1 divided by the input, -7 in this case. Well, positive divided by negative is negative, so that of course is the same thing as -1/7. And -1/7 is the opposite of R of 7. I guess 7, okay. R of the opposite of 7 is equal to the opposite of R of 7. So again, that's the defining concept of an odd function. Okay, we'll leave it at that. So that's an odd function. Now, I didn't actually prove this was an odd function. I demonstrated that it could be, because at least in one case it turned out that way. Math is not really a science in the typical sense. So in science, the idea is you have to be able to discover something and replicate it and show that it seems to always be the case. And so normally if you, for example, were to mix hydrogen and oxygen together with a little bit of maybe a spark of electricity, and you get water, and you try that again, and you try it again, and you maybe vary the parameters a little bit, and in every case it seems like you're getting water. You make a conclusion that somehow there's a connection there, that maybe water is made out of hydrogen and oxygen. And that's science, physics, chemistry, that sort of thing. In mathematics, you'd have to go a little bit beyond that, where you don't just experiment and show that this seems to always happen. You have to show that it must happen and that nothing else could possibly happen. So what I'm saying is, if we were to go ahead and take my function R of x equals 1/x and plug in more and more numbers, we did this a million times, that still wouldn't prove that this is an odd function, even if it seemed to be odd every time it happened. Mathematicians aren't satisfied with that. They want to be able to prove it. Turns out to be not that hard to prove this. We could, for example, just look at, copy and play around a little bit with this. So if we were to look at a generic input of, let's say, A, R of A is equal to 1/A. And that's true whatever the input is. Of course, the domain of this particular function is everything other than 0. You can't divide by 0. 1/0 doesn't mean anything. It's a totally meaningless concept. So within the limitations of that domain, any other real number you can plug in here and you get the reciprocal. Well, if I try with the opposite, so copy that and just make a little change. I replace A with its opposite. We get something very similar to what I had with 7 before. R of the opposite of A is equal to 1 over the opposite of A. So far it looks like, and then of course it can be shown regardless of what A is. Well, A is either a positive number or a negative number. And if you take 1 and divide it by the opposite of A, well, if A is positive, then the opposite of A is negative, and then 1 divided by the opposite of A will be a positive number, and we get the opposite of that. I think I said that right. I got sort of lost halfway through my thought here. So if A is positive, the negative of A, opposite of A is negative, and then you have 1 divided by a negative, which is negative, and it'll be the negative of 1 over A. On the other hand, if A happened to be negative, then its opposite is positive. But then 1 over A would be negative because A is negative, and then the opposite of that whole thing, which is what's represented by the negative in front of this, is going to be a positive number. I know a lot of words there. Math isn't meant to be a spoken language. Anyway, what I've shown here is that for any input A, not just 7, but whatever you're looking at, R of the opposite of A is equal to the opposite of R of A, and that's what's meant by the term odd function. So I just proved, more or less, that the reciprocal function is an odd function. Okay, so that's enough of that for now. Maybe I'll briefly mention once again that the odd functions have the property that if you look at their graphs, it has a sort of double symmetry in the sense that if you were to look at reflecting it left and right, and then after that, reflecting it top and bottom, you get right back to what you started with. And that's true for the function y equals 1 over x. If you're not familiar with that, then I encourage you to go look up the graph, or maybe try creating the graph yourself and see that 1 over x does have odd symmetry. It's symmetric with respect to the origin of the coordinate system. Another way you could sort of look at that is if you rotate the graph 180 degrees and it's still the same graph you started with, well, it has that sort of symmetry. Okay, so that's our video for now.